Hello everyone. We are delighted to present our work entitled Towards Plug-and-Play Visual Graph Query Interfaces, Data-Driven Selection of Canned Patterns for Large Networks. This is a collaborative work between NTU, Fu Den University, Postec, and Hong Kong Baptist University towards realizing plug-and-play visual query interfaces. The world is full of networks. The end users of networks are not only techies who may possess the esoteric knowledge of graph query languages to query graphs, but domain experts such as biologists, security analysts, chemists, social scientists, journalists, financial analysts, and many others. Given the diverse end user base, indeed a recent survey by Sahu etc. reported that query languages and usability are the top challenges in graph query processing. A popular way to alleviate this challenge is the deployment of direct manipulation-based visual graph query interfaces. Such interfaces are easy to learn, use, and retain. They appeal to novice users, are easy to remember for intermittent users, and can support rapid query formulation for frequent users. Let us say we wish to formulate subgraph matching queries on the Amazon network. We have a GUI that enables direct manipulation-based query formulation. However, a user may not necessarily have a specific pattern in head when they explore a network. In this case, what will be the topology of her query? The network looks like a giant hairball and it is hard for anyone to visualize the structures within it. Even if we consider the building blocks of networks such as triangles, wedges, and rectangles, they occur in almost all large networks and hence do not reveal anything specific to the Amazon network. It would be helpful if we can provide a small set of topological structures in the underlying network on the GUI for the user to choose from. We refer to them as canned patterns. Canned patterns open up the opportunity for efficient visual query formulation. Pattern at a time mode typically incur fewer steps and lesser time in formulating queries compared to edge at a time formulation mode. Furthermore, it reduces frustration of drawing an edge repeatedly in edge at a time mode, especially for larger queries. Last but not the least, canned patterns support both top-down and bottom-up search. The former refers to visual querying when a user has a specific pattern in mind to query. The latter refers to scenario where a user does not have any upfront knowledge to begin search on a network. The key question we address in this work is how we can select the canned patterns from a large network. We refer to this as the canned pattern selection problem. Data-driven selection of canned patterns paves the way for plug-and-play visual subgraph query interfaces. Such interfaces enable efficient creation, maintenance, and portability of GUIs across different application domains and sources. Assume we have 3 different network data in different domains. Each one of them is like a socket. A plug specific to each socket can be generated by customizing components in the GUI accordingly, such as selecting a set of canned patterns relevant to the network. Let us now define the canned pattern selection problem, which is at the heart of realizing plug-and-play visual graph query interfaces. Given a network, a visual graph query interface and a user-specified plug, the goal of the canned pattern selection problem is to select a set of unlabeled patterns for display on the interface which satisfies the plug specification and optimizes desirable characteristics of the canned pattern set. We define plug as a collection of attribute value pairs that specifies high-level content of a canned pattern panel in a GUI. Note that we focus on unlabeled patterns as they facilitates both visual formulation of the subgraph enumeration problem and the subgraph matching problem. We follow the definition of desirable characteristics of canned pattern set proposed in the work of Huang etc. In particular, these characteristics are high coverage, high diversity, and low cognitive load. That is, the canned patterns should ideally cover as large portion of the network as possible, are structurally diverse and requires minimal mental effort by user to browse and select. Huang etc. has shown that the CPS problem is NP-hard by reducing it from the classical maximum coverage problem. At first glance, it may seem that we can select the canned patterns from query logs in order to address the CPS problem. However, query logs are frequently unavailable. In some application domains, query logs-driven approach may not be feasible as it is a chicken and egg problem where query logs do not exist. Hence, a middle ground approach leveraging real-world query log analysis could be more appropriate. A recent work from Bonifati etc. highlighted the presence of certain topological structures such as path, tree, star-like, cycle-like and flower-like subgraphs in real-world queries. In this work, we propose a framework for data-driven selection of canned patterns for large networks called TATU. TATU is designed to generate candidate patterns whose topology are similar to the ones reported in Bonifati's work. The TATU architecture consists of two main components, namely, the candidate pattern generator and the canned pattern selector. Briefly, the candidate pattern generator takes in as inputs a large network and the user-specified plug. The candidate patterns generated are then used as inputs by the canned pattern selector, which selects the final canned patterns and expose them to the GUI. In candidate patterns generation, truss-based graph decomposition is used to transform the input large network into a dense truss-infected region and a sparse truss-oblivious region. Then, K-chord patterns are generated and their corresponding frequencies obtained. The composite chord patterns and their frequencies are then generated. The K-chord patterns and composite chord patterns are flexible K-truss-like patterns that are useful for constructing petal and flower queries reported in Bonifati's work, as these queries often contain triangle-like structures. Next, star extraction on the truss-oblivious regions is used to further decompose the graph. This gives rise to stars and asterism patterns and also a remainder graph. From the remainder graph, small patterns are extracted. In canned pattern selection, first, candidates are pruned based on their frequencies. For the remaining candidates, each is considered to be added to the canned pattern set at a time. The coverage, cognitive load, and similarity values are computed and used to determine the pattern score. In the first iteration, the candidate with the best pattern score is selected to be added to the final pattern set, and this score is saved as S-best. In subsequent iterations, TATU goes through the same steps. However, instead of greedily selecting the candidate with the best pattern score, it randomly chooses the next pattern from amongst candidates that are sufficiently good. Note that this approximate algorithm achieves 1/e approximation of the canned pattern selection problem. The final canned pattern set is built up iteratively until when the required number of patterns is achieved or when there are no more good candidates. We have conducted exhaustive user and automated study to understand TATU with respect to state-of-the-art techniques. Please peruse our paper and technical report for detailed experiments on various issues. Here we answer 3 key questions. First, do canned patterns generated by TATU enable superior query formulation time? Second, do canned patterns generated by TATU enables fewer steps for formulating a query? Third, is TATU efficient on large networks? The first 2 questions impact efficient visual query formulation, whereas the third question is critical for its usage in practice. We observed that TATU has superior query formulation time compared to 6 other baselines. These baselines are edge-at-a-time approach, default patterns, random patterns, graphlets, frequent patterns, and catapult-generated patterns. Note that the frequent patterns are generated using the Peregrine tool. In particular, it is on average 9.7 times faster than edge-at-a-time approach. TATU also has superior query formulation steps. Compared to edge-at-a-time approach, TATU requires 18 times fewer steps on average. We examined both the candidate pattern generation time and the runtime of TATU. Across different datasets we tested, generation of chord-like patterns is the most expensive. This is due to the check of edge mergers in composite chord patterns. The runtime of TATU consists of 3 components, namely, truss-based graph decomposition, candidate generation, and pattern selection. The component with the dominant runtime varies across the dataset. Based on the figure, we can see that TATU can efficiently generate and select canned patterns within a few minutes. In conclusion, TATU is a novel framework for data-driven selection of canned patterns for large networks. It facilitates efficient visual subgraph query formulation and is an enabler for both top-down and bottom-up search, playing a key role in realizing plug-and-play visual graph query interfaces. We have reached the end of our presentation. Thank you very much for your attention.